Hi guys, welcome to video lecture number 3. In the last video, we talked about how to describe atoms by using their atomic number, their mass number, and their net charge. Before we go on to learn about how these ways of describing atoms are related to the periodic table, I want to take a moment to talk about models. Don't make the mistake of thinking that just because we're learning about atoms that we're describing them exactly as they are. Scientists use models to represent how things are or how something works based on the results of their experiments. But scientific models change over time based on new evidence. So what is a model? A model is simply something that represents something else. A toy car represents the real thing. A globe of the Earth represents the actual Earth. A speed graph represents the actual motion of an object. Every model has some advantages or ways of helping us understand the real thing better, but it also has limitations. For example, if you're trying to learn about the size of the Pacific Ocean, a globe can help you understand that better because you can see it in comparison to the continents and the Earth in general. But that globe can't tell you how deep the Pacific Ocean is, which is one of its many limitations if you're trying to learn about the ocean. In the same way, as we look throughout history at different ways and different models that scientists have used to describe atoms, bear in mind that the models they used had advantages and limitations, just like the ones that we use today. People have been curious about the world around them and what it's made out of for a very long time. So our discussion takes us way back in history. Before science was even a thing, there was a Greek philosopher named Democritus who lived about 2,500 years ago. And Democritus conducted a thought experiment. He said, what if I could take something that's made out of matter and divide it in half? And what if I took that half and divided it in half again, and again, and again? You get the idea. Democritus reasoned that if you divided something enough times, eventually you would get to a piece of that object so small that it would no longer be divisible. He called that small particle atomos, which is where we get the word atom. Now, Democritus thought that everything was made of atomos, and that different atomos, or atoms, had different properties based on what they were. So, for example, a stone might have atoms that were very, very hard and had jaggedy edges, were difficult to separate. Or he thought that salt atoms must be very sharp because salt has a bitter taste. Now, Democritus' ideas didn't really catch on because of a guy named Aristotle, who was a big deal in Greece at the time. Aristotle thought that all matter was made of earth, fire, air, and water, and his ideas were accepted and hung out for a long time. But Democritus, through his reason alone, was surprisingly close to the truth. It wasn't until the 19th century that the idea of atoms was really re-examined. During the Enlightenment, science was beginning to resemble what we think of today. During this time, many of the greatest minds of Western civilization were beginning to explore the world through observation and experiment instead of just philosophy. John Dalton was an English chemist and physicist who revisited the idea of the atom, but unlike Democritus, he backed up his ideas with good experimental evidence. Dalton thought of atoms as solid spheres of matter that resembled billiard or pool balls. He spent a lot of time performing chemical reactions, and unlike Democritus, he didn't think that every kind of matter had its own atom, but that different elements combined to form different substances or compounds. For example, Dalton was able to separate water into oxygen and hydrogen gas during chemical reactions, showing that instead of being made out of water atoms, water was actually a combination of different kinds of atoms that only had the properties of water when they were combined. The atoms had completely different properties when they were separated. Water is a liquid that you use to put fire out, but it's actually made out of gas atoms that are highly explosive. In a lot of ways, Dalton's billiard ball model is really useful. Thinking of atoms as little round spheres is an especially easy way to model chemical reactions. In fact, we'll use his model when we study chemical reactions because it's fast and it's simple. But Dalton's model had limitations too. It didn't explain how atoms combined to form compounds, and like Democritus, Dalton thought atoms were the smallest particles of matter. Almost another 100 years would pass before subatomic particles were discovered. In 1904, another English physicist named Joseph John Thomson was experimenting with cathode rays. If you have no idea what a cathode ray is, think of a really old-fashioned television or computer monitor. The ones that are all boxy instead of being a flat screen. The picture on those screens is produced using cathode rays, which are basically a beam of electrons. J.J. Thomson knew cathode rays were made of particles that had mass, but they couldn't be made of atoms. He was able to calculate that they must have a much tinier mass than atoms, that they must be even smaller or subatomic. So Thomson was credited with the discovery of the first subatomic particle, the electron. You know by now that opposite electrical charges attract each other and like charges repel each other. Thomson knew this too and was able to prove that electrons were negatively charged with a very simple experiment. He shot a cathode ray in a sealed glass vacuum so that it passed between two electrically charged metal plates, one positive, the other negative. The cathode ray changed its course or bent towards the positively charged plate and away from the negatively charged plate, proving that electrons must be negatively charged. Because the atoms in their elemental forms are electronically neutral, Thomson knew they must have a positive charge somewhere to cancel out his negatively charged electrons. So he thought of atoms as a plum pudding. The pudding was the positively charged atom, and the plums were the negatively charged electrons dispersed throughout the pudding. You probably have no idea what a plum pudding is, since it isn't 1904 and we aren't in England. It might be more useful to think of something like a blueberry muffin. Thomson thought that an atom was kind of like that, a positively charged sphere, the bread part of the muffin, with negatively charged electrons inside, just like the blueberries. In 1911, a New Zealand physicist named Ernst Rutherford proposed a new atomic model. Rutherford conducted some brilliantly creative experiments. We often have the misconception that scientists make discoveries only when the results of their experiments confirm their hypotheses to be true. So, a lot of the time, I see students trying to make their observations support their hypothesis, even when they really don't. If you set up an experiment well, don't be afraid of results that are unexpected or opposite of what you thought would happen. Sometimes weird results lead to great discoveries. That's what happened to Rutherford in his most famous experiment. He had already won the Nobel Prize in 1908 before he conducted his famous gold foil experiment. What he did was shoot alpha particles, which are 2 protons and 2 neutrons bundled together, although he didn't know that since neither particle had been discovered yet. Anyway, he shot alpha particles through an ultra-thin sheet of gold foil, surrounded by a screen that could detect where the alpha particles went. Now, Rutherford accepted J.J. Thomson's plum pudding model of the atom, a positively charged sphere with electrons embedded throughout. He expected the alpha particles to go right through the gold atoms, but amazingly, some of them didn't. Instead, they bounced off to the side, or even ricocheted back towards the particle emitter. Why is this amazing? Because it was completely an unexpected result. With Thomson's plum pudding model, shooting an alpha particle at a gold atom was kind of like shooting a handgun at a blueberry muffin. You would be pretty surprised if the bullet didn't go straight through the muffin, and you would be very surprised if it glanced off or bounced back at you. If that happened, you would probably conclude that there was something else in the muffin besides blueberries. That's how it was for Rutherford. He meant to confirm Thomson's model of the atom with his gold foil experiment. But instead, his results suggested that atoms were actually very different. There had to be something really hard and dense in the atom to deflect those alpha particles. Rutherford also thought it had to be a really small part of the atom, because only some of the particles were deflected. What he proposed in the end was the nuclear model of the atom, a dense, positively charged nucleus at the center that had most of the atom's mass, with electrons flying around the nucleus in orbits. Niels Bohr was a Danish physicist who added to Rutherford's nuclear model. Bohr's research led him to conclude that electrons moved around the nucleus of the atom in distinct orbits, depending on how much energy they had. Bohr confirmed that the further electrons were from the nucleus, the more energy they possessed. The first orbit or shell could hold only 2 electrons before they started to form a new energy level. The second and third shells or energy levels could hold up to 8 electrons each. The Bohr model of the atom was a breakthrough because it introduced a structure to the electrons around the nucleus. And it was easy to understand because that structure closely resembled the planets of the solar system orbiting the sun. The simple structure of the Bohr model's electron orbits is really useful for understanding how atoms bond together to form compounds like water, because chemical bonds are actually formed when atoms exchange or share electrons. The Bohr model is also beginning to resemble the model of the atom that we think of in this class. The last and the current model of the atom, the quantum model, is a bit more strange. Lots of scientists contributed in the development of the quantum model of the atom, but maybe none more than Erwin Schrödinger. Schrödinger realized that while Bohr's idea of nice and neat planetary electron orbits was useful, it was overly simplistic. Electrons don't actually orbit the nucleus like planets around the sun. Schrödinger showed that they're found in 3-dimensional orbitals around the nucleus that take on a variety of shapes. In fact, a lot of the shapes sort of look like balloon animals. The strange thing about Schrödinger's model is that the shapes that make up the electron cloud only represent where an electron could be found, not where it actually is. You see, Schrödinger found out that electrons are really weird. Scientists can't really find out where they are in an atom. If we try to measure the position of an electron, or where it is, then we also change where it is too. It's almost like trying to measure the length of a table only to have the table grow longer or shorter to fit your measuring tape. So since Schrödinger couldn't tell exactly where electrons were, he did the next best thing. He described where they probably were. For example, this purple circle near the nucleus represents where the first 2 electrons might be found. The next 2 would be somewhere in these 2 red shapes. The next 2 would be in these other red shapes, and the last 2 would be somewhere in this gray sphere. This is the only time in this class where we'll look at the quantum model of the atom, and I don't want to confuse you. The reason it's important is because the quantum model is the first atomic model that really represents electrons in an electron cloud. Just because we'll use a model that has orbits for electrons, I don't want you to forget that the electron cloud is 3-dimensional and that electrons move around in a sort of controlled chaos, not in tidy little orbits. Okay, so in addition to the electron cloud, the quantum model also has a complete nucleus, made up of our final two subatomic particles, protons and neutrons. Our friend Ernst Rutherford discovered the proton in 1919, and his student, James Chadwick, discovered the neutron last of all. I hope that by seeing how scientists have changed their ideas about the atom throughout history, you have a better understanding of atomic structure, but also how scientific models change over time. Each model we talked about has advantages and limitations and was based on the evidence that was available. I'm sure that new evidence will be found and that our ideas about atoms are still incomplete. In this class, we will sort of mix two of these models together and sometimes even return to Dalton's model for simplicity. The quantum model of the atom has the best or most accurate representation of the electron cloud. But representing the electron cloud as fields of probability is pretty confusing when you're trying to model chemical reactions and bonding, which is what we will do in this class. So instead, we'll stick to representing the electron cloud with the planetary Bohr model, where the first energy level can hold 2 electrons and the second and third can hold up to 8. We will use the nucleus of the quantum model, however, because we need to know how many protons and neutrons are in the nucleus of atoms. In the next video, we'll learn how the periodic table is related to atoms and describes them using atomic number and atomic mass. We'll begin to use the periodic table to create atomic models like the one on the right. If we stick to an atomic model like this carbon atom, we have a detailed enough picture to study the periodic table and chemical reactions that's still simple enough to understand in the very limited time we have to study chemistry. See you next time.